Hello, ladies and gentlemen. This is Miss Bashauer. We are going to be starting notes for lesson 3 today. Lesson 3 is going to be all of the different, all of the different operations that you can possibly do when you are talking about radical functions and simplifying radicals, okay? So this is going to come from actually 2 sections today in our old textbook still, but basically I want you guys to understand that we're going to be adding and subtracting as well as multiplying and dividing, okay? And very, very often, just like when we think about other instances when we're adding and comparing that to multiplying and dividing, there's going to be different rules depending on if we are adding and subtracting versus multiplying and dividing. Okay, it says, we're going to start with adding here, guys. We're going to start with adding and subtracting. That'll be the first part. The basic idea is we need to understand like radicals. Okay, when you add and subtract in algebra with things that have variables, we have to have like terms, okay? 2x plus 3x is like terms. 5a and 7a, those are like terms. They have to have kind of the same piece towards the end that is the same. What's cool is that radical functions are going to do the same thing, okay? So we're looking for like radicals. As you can see here, we have the square root of 5 and the square root of 5. We have the square root of x and we have the square root of x. We have the square root of 4t and 4t. Okay, I know those look a little bit funny. Sometimes it's hard to get the graphics to put the little top on there like I'd like. But the idea is still there. We have to have the same piece towards the end if we're going to add or subtract radical terms. Okay, on the other hand, these are not like radicals. I have 2 and the square root of 15. I have 6 times the square root of x and the square root of 6x. Now that's a fun one, okay? Do you see how this piece and this piece are not the same exactly? So just be very careful. Same with our third example here. 3 times the square root of 2 and 2 times the square root of 3. The piece that is in the inside, you might call that the radicand, is not the same, okay? They have to be the same in order to add and subtract radical functions, okay? Only like radicals can be combined for adding and subtracting. It's just like when we do algebra. 6x and 3x is 9x, okay? How might this work? 6 times the square root of 3 plus 3 times the square root of 3. Do they have like radicands? Do they have this piece that's behind that's the same? Well, of course. So how are you going to add them together? You're just going to add this front piece with this front piece and get 9. Okay, so your final answer would be here. 9 times the square root of 3. Okay, which is exactly how we do it with algebra. We have 6x, 3x, we get 9x. Okay, that second piece, that part at the end just kind of comes along. It's the same with radical functions. This piece here, the square root of 3, square root of 3, square root of 3, just kind of comes along, and we add together the front pieces, okay? So this is adding or subtracting. There's some very, very basic options here. I can go through a few of them with you. We might not do all of them in the sake of time, but we can do all of them tomorrow in class. So if you feel like kind of trying some out on your own, try them now, and we'll check them over in class tomorrow. 5 times the square root of 7 minus 6 times the square root of 7. First thing you want to ask yourself, are the radicands the same? In this case, yes, they are. Therefore, I can add them together. The pieces that I'm going to add or subtract, remember addition and subtraction, just opposite operations, are the pieces that are in front. 5 minus 6 is -1 times the square root of 7. Okay, but I thought we couldn't have negatives involved with square roots. Well, you can have them in front. You can multiply -1 times the square root of something else. Okay, could you have 1 times the square root of -7? Well, no, that's when we have a little bit of a problem. But you can have a -1 out in front. That's not a big deal. Okay, this one is very similar. Why don't you try that one on your own if you feel like it? The second one here has to do with what happens when there's a variable inside. Same exact idea, guys. Is it the same? Square root of n, square root of n? If it is, you can add together. 4 plus 4 is 8 times the square root of n. Okay, be careful. With this last example here, it looks to me like there are only 2 like terms. Okay, those could get added together. Remember, ooh, lots of tricky pieces in here. If you don't see a number in front, put a 1. So I have -1 and I have +9 with like terms. So that would make me, I guess, +8 root 5s. And then can this one get added together? Well, I don't really think so because it's a 2s and a 5s. The things that are underneath are just a little bit different, so be careful. Square root of 2s plus 8 root times 5s. Okay, so that's the basic idea of adding and subtracting. We have lots of different things we could add or subtract. Sometimes you're going to get a problem looks like this. Actually, these are a lot more fun. When you have a problem like this, the directions up here say be careful to simplify expressions before you add them, because this 45 and 20 look like very different radicands. Those don't look like they're the same, but you might find something interesting if you simplify them. In 45, I'm going to change that. Remember, I'm always looking for perfect squares. I'm going to look at 45 as 9 times 5 minus 20. I'm going to kind of look at that as 4 times 5. So what happens here? Perfect squares of 9 and 4. Those can kind of come out, meaning that I can apply the square root to them. And when I find the square root of 9, it would be 3. Okay, the square root of 9 is 3. So this turns into 3 times the square root of 5 minus, what happens with the 4? The square root of 4 is 2, right? So this is 2 times the square root of 5. And now, after just a little bit of work, you can see that, yay, you have like radicands. Okay, these are like radical terms. You can put them together. 3 minus 2 is 1. 1 times the square root of 5. Okay, do you really need to write the 1? Nah, you can just write square root of 5. Okay. All right, we have some other options here. Let's try one more, and I'll leave you the third one to try your own if you'd like. Same thing, let's simplify. If I'm looking at 9 root 75, oops, I don't want to write 75. I want to write 25 times 3 plus, oopsie, I forgot the 2. 50, I don't want to write 50. I want to write 25 times 2. As you can see, hopefully, maybe I would get like terms. The 25 can come out as a 5. So I would get 45. 5 times 9 makes 45. Times the square root of 3 plus 25 again can compound as 5. And now I get 10 times the square root of 2. And oh, I think they were trying to be tricky here. Okay, just because this 25 here that I pull out is the same doesn't mean that I end up with like radicals there. So if it asks you to simplify, you still need to do this step and you still need to do that step, because this one is still more simplified than what you started with. But I can't really go any further because one radical term has a 3 and one has a 2. Okay, so this is basically adding and subtracting. Let's keep going on. You can try that last one if you want. We have some more group practice here. What I will do is I will work through these and I will put a little picture on Haiku if you want to check them over, or you can do them and check them over with me. Some of you might have a substitute. You check them over with that person, but give some of these a try and then you'll feel real good about adding and subtracting. Let's move on to multiplying. What's interesting about multiplying is that when we added and subtracted, when we add and subtract, we need like terms, just like any other type of problem with algebra. What about when you multiply or divide? You don't need like terms, which is kind of cool, and that at least the rules are consistent. So we did this a little bit, I think, in our first lesson. If you're multiplying here, the square root of 8 times the square root of 6 is just the square root of 48. Okay, continue to simplify, obviously, and maybe you would have wanted to simplify that 8 first. Let's see if that will give us the same type of answer. The square root of 8 is 4 times 2 times the square root of 6, and this 4 can come out, so I have 2 times the square root of 2 times the square root of 6. Okay, can I continue? You betcha. I do not need like terms. I can multiply those, and I can get 2 times the square root of 12. Okay, sometimes when you multiply, it doesn't actually help you simplify as far as maybe we still have some stuff in here that I can take out. We have 2 times the square root of 4 times 3 because 4 is a perfect square, so the 4 can come out and we get 2. 2 times 2 is 4. 4 root 3 would be your answer on that one. Okay, so what's important is this kind of idea over here that when you multiply or divide, like terms are not needed. Okay, what about this one? 2 times the square root of 5 times itself. What is that going to look like? 2 times the square root of 5 times 2 times the square root of 5. Okay, it's kind of like, well, it's not really like FOILing. I shouldn't say that. It is not like FOILing. If there was a plus or minus in between, because we'll get to that in a different, not here yet, but we'll get to that eventually. But basically, you kind of have to multiply this piece times this piece and this piece times this piece. Okay, when you do the green part, you're going to have 2 times 2 is 4. When you do the pink part, you're going to have the square root of 5 times the square root of 5. Well, the square root of 5, wouldn't that be the square root of 25? And what's cool about that is a perfect square. The square root of 25 is just 5. So, hopefully you can see that your final answer turns out to be pretty nice. It's just 20. Okay? So that's how you'd go about if you have kind of 2 pieces and parts in there. What happens with this last one? We'll do all of these. This is just kind of the introduction to multiplication. We should do them all. So now we have the square root of 3y times the square root of 12y. Okay, you can think about doing kind of the coefficients in front first if you want. 3 times 12 is 36. Y times y is y squared. And so then your final answer, both of those are perfect squares. Square root of 36 is 6. The square root of y squared is just y. Okay, so again, that one turns out pretty nice too. Okay, so that's the basic idea of multiplying and dividing. You don't need like terms. But we've done lots and lots of different types of multiplication. We've done the distributive property. Okay, what's going on there? Well, when we multiply and we have some parentheses here, it's going to be the same basic idea as when you distribute with variables. Multiply this one times this one and that one times that one. Alrighty, we're going to get 3. Square root of 3 times 7 is just 7 times the square root of 3. There's not too much you could do with that. Minus the square root of 3 times the square root of 8 is the square root of 24. Okay, remember, you're not done until things are simplified as much as possible. In 24, I can look at that as 4 times 6. So I have 7 root 3 minus, let's just take our time writing out our steps so we can see where everything comes from. And I can bring out the 4. Square root of 4 is 2. 7 square root of 3 minus 2 square root of 6. Oh, I was so hoping that those would be like terms we could continue, but it doesn't look like it. So I'm done. Okay, nothing more you can do there. All right, we have some more distributive property problems. Why don't, I'll do this one with you. I'll do the next one, and then maybe you guys can attack that last one. Square root of 2 is what I'm distributing, and I'm going to need to multiply that by both pieces. Why? Because you have some parentheses here. If these were like terms, you could put them together first. Are they like terms? I guess I have an 8 and an 18. Would they turn into like terms, I wonder? I don't know, maybe. Should we try it? Maybe we should simplify these first. Let's give it a whirl. Okay, the square root of 2 times square root of 8 turns into 2 times the square root of 2 if I take out the 4, and this one would be 9 times 2. So that would be 3 times the square root of 2. Oh, that's cool. So there's always different ways to do that. When you simplify these, they turn into like terms. You could do that first. You don't have to distribute if you can actually put this stuff together. So why don't we put it together? 2 times the square root of 2 plus 3 times the square root of 2 is going to be 5 times the square root of 2 multiplied by the square root of 2. Okay, this just has to get brought down. I haven't really done anything with it yet. And now, how am I going to multiply those? Well, it's kind of like having a 1 here. So 1, oopsie, that's not what I wanted. 1 times 5 is just 5. And the square root of 2 times the square root of 2 is 4, which is, when you bring this out, a 2. 2 times 5 is 10. Okay? Kind of fun when something that starts out kind of complex turns into something nice and easy like 10. Okay, so this is another just piece of how we multiply different things that come up. We can use the distributive property. Not only can we multiply with the distributive property, we can FOIL. Okay, we can FOIL. Isn't that cool? So if you were to be given a problem like this is just multiplication, but these aren't like terms. I can't put them together. These aren't like terms, so I can't put them together. This is really almost equivalent to writing something like 4 minus 3x times 3x plus 5. Okay, if I were to show you that, can you put that together? Can you put those together? No. So what do you have to do? You have to FOIL. You thought you were all done with FOIL. It's back. All right, so when I FOIL these, the first ones are going to be 4 times the square root of 3. The outers, okay, those were the firsts. The outers are going to be 4 times 5 is 20. The inners are going to be here. Square root of 3 times the square root of 3 is the square root of 9, which is actually just 3. Okay, maybe you've noticed that when you do the square root times itself, you end up getting that number without the square root, because square root of 3 times the square root of 3 has to be square root of 9, which is eventually 3 itself. Okay, so I am going to subtract 3 when I do the inners. Subtract because I have a negative there. And then I have another set of outers. Oh, wait, I did the outers. So sorry. Oopsie. I got excited. We're on the L of last, right? So that would be minus 5 times the square root of 3. Okay, I'm going to erase this because it's getting a little sloppy. Any like terms here? Looks to me like these are like terms. So that would be plus 17. And then I have the other pair. Are they like terms? They really are, because I have the square root of 3 and the square root of 3. So 4 minus 5 would be negative 1 times the square root of 3. Okay? And it looks to me like that is my final answer. Again, there's a bunch of example problems here. You guys can try some of those. I'll get some answer keys to those out to you so you can check them as you go. Look on Haiku for those. But try these. Try them. Give them a try. The last slide, maybe you noticed I skipped it. This one is all about kind of one of those random rules of when something is simplified. Okay? A quotient with a radical in the denominator is actually not simplified. We went through this a little bit in class already to kind of preview it, but I want to formally teach it to you. Here's the idea. If you get an answer that looks like this one, unfortunately, this is a no-no. You can't have a square root symbol in the denominator of a fraction. Okay, so to simplify, what do? To simplify, multiply by a fraction with that rational expression in both the numerator and the denominator. So what is the problem here? I have the square root of 2. So to my fraction, I'm going to multiply by this square root of 2 over the square root of 2. Why is that okay? How come I can just do whatever I want? Well, really, you're multiplying by the square root of 2 over the square root of 2 is simply something that's equivalent to 1, right? Anything that's the same in the bottom as the top is 1. 4 over 4 is 1. 10 over 10 is 1. So if I multiply a fraction by 1, I haven't changed what the fraction is saying. I'm just making it look a little different. Okay? So what happens? The square root of 2 times the square root of 2 ends up being the square root of 4, which is just 2. And now, on the top, I do the same thing. I'm going to multiply across. 1 times the square root of 2 is simply 1 times the square root of 2. I don't need to write the 1. So what I've essentially done here, folks, is I have gotten rid of the fraction in the denominator. I'm sorry, not fraction, I'm so sorry. The radical sign. I've gotten rid of this square root symbol in the denominator. And now I just have a 2. Okay, another example might be something like this. The square root of 11 over the square root of 3. What am I going to multiply by? Well, I think that I'm going to write this problem over here just to make it a little bit clearer. I'm going to multiply by something that is equivalent to 1 because that won't change the problem. Well, what is that something that I'm going to multiply by? I'm going to multiply by whatever is being problematic down here. I'm going to multiply by the square root of 3 over the square root of 3. Why do that? Because it has the result that I want. It will make the radical symbol in the bottom go away. So in the top of my fraction, I'm just going to multiply across. I get the square root of 33. And on the bottom, I get the square root of 9. The square root of 9 is just the perfect square 3. Okay, and then here I get the square root of 33. There's not really much I can do at that point, but I have solved the problem of this nasty radical symbol, square root symbol in the denominator. Okay, so bring questions if you have questions. Do a little bit more practicing if you're going to do, if you want to try some of these problems here. And then with that, we will be all set. We'll do these practice problems next. Okay, have a great afternoon. I will see you later.